It can power entire countries for years, and yet, the same element can become a global disaster if even one thing goes wrong. This element was forged in the death of a star billions of years ago. This is uranium, and most people have no idea how deep the story goes. Before uranium was a fuel, before it was a weapon, it was a catastrophe. When a massive star runs out of fuel, it doesn't just die quietly, it explodes in a supernova, one of the most violent events in the universe. And, in that split second of unimaginable energy, heavy elements like uranium are forged and hurled across space. About 4.5 billion years ago, that debris collapsed into our solar system. Uranium sank deep into the forming Earth, rare, radioactive, and slowly decaying. Today, only about 2.8 parts per million of Earth's crust contains it. That rarity is exactly what makes it so valuable. The country that controls the most uranium isn't Russia. It isn't the US. It's a landlocked nation most people couldn't point to on a map. Kazakhstan produces roughly 43% of the world's uranium. Canada and Namibia follow closely, with Australia holding the largest known reserves on the planet. But why these places? Uranium concentrates in ancient geological formations, sandstone basins, granite intrusions, and areas where groundwater once moved through rock over millions of years. Canada's Athabasca Basin in Saskatchewan is the richest high-grade uranium deposit on Earth. Namibia's Rosing mine has been running since 1976. Geography, geology, and time. Those are the three things that decide where uranium ends up. You don't always need to dig to mine uranium. Sometimes you just pump it out of the ground like water. There are three main methods. Open pit mining works for shallow, low-grade deposits. Massive excavations, heavy machinery, and enormous volumes of rock moved. Underground mining goes deeper, targeting high-grade ore bodies like those in Canada. But the most modern method is in situ recovery, or ISR, where a chemical solution is pumped underground, dissolves the uranium from the rock, and is pumped back to the surface. No blasting, no tunneling. Kazakhstan uses ISR almost exclusively, which is a big reason it dominates global production. Each method has trade-offs in cost, safety, and environmental impact. The uranium that comes out of the ground is completely useless as fuel. It takes an industrial process spanning multiple countries to turn raw ore into reactor fuel. First, the ore is crushed and chemically processed into yellowcake, uranium oxide, or U3O8. It looks like mustard powder. From there, it's converted into uranium hexafluoride gas, then sent to an enrichment facility where the concentration of the fissile isotope U-235 is increased. Natural uranium is only 0.7% U-235. Reactor fuel needs 3 to 5%. Weapons grade needs over 90%. After enrichment, it's converted into ceramic pellets, loaded into metal tubes called fuel rods, and assembled into fuel assemblies ready for a reactor. The entire supply chain spans mining, milling, conversion, enrichment, and fabrication, often across 5 or 6 countries. 1 kilogram of uranium fuel contains as much energy as 3,000 tons of coal. Uranium has 2 main isotopes, U-235 and U-238. U-235 is the one that fissions. When a neutron hits its nucleus, it splits, releases enormous energy, and fires out more neutrons, triggering a chain reaction. That chain reaction, controlled inside a reactor, is what generates heat to produce electricity. U-238 doesn't fission easily, but it can absorb neutrons and transform into plutonium-239. Another fissile material. This is both useful in some reactor designs and concerning from a non-proliferation standpoint. Nuclear energy is the only low-carbon power source that can run 24 hours a day. 365 days a year, regardless of weather. And almost nobody talks about it that way. Inside a nuclear reactor, uranium fuel rods heat water. That steam spins a turbine. The turbine generates electricity. It's the same basic process as coal or gas, except uranium produces no direct carbon dioxide during operation, and one fuel assembly lasts about 18 months. A single nuclear plant produces as much electricity as thousands of wind turbines on a fraction of the land. The main waste challenge is spent fuel, highly radioactive but compact. All the spent nuclear fuel ever produced in the US would fit inside a single Walmart. The scale problem is smaller than most people think. The most dangerous part of nuclear power isn't the reactor, it's the mine. Uranium mining leaves behind tailings, the crushed rock waste after extraction. Tailings contain radioactive elements like radium and thorium and can leach into groundwater if not managed properly. Radon gas, a radioactive decay product, is a genuine health risk for miners without proper ventilation. Modern operations have strict regulatory standards: line tailings ponds, radiation monitoring, site rehabilitation plans. But legacy mines in Central Asia, Africa, and the American Southwest left contamination that still affects communities today. The environmental story of uranium isn't black and white. It's about whether the rules are enforced. Russia controls a significant portion of the global uranium enrichment capacity. That's not a theory. It's a supply chain vulnerability Western governments are only now scrambling to fix. Kazakhstan produces most of the world's raw uranium, but Russia's state company Rosatom processes a large share of the world's enrichment services. After the 2022 invasion of Ukraine, Western nations suddenly realized how dependent their nuclear fleets were on Russian enrichment. Meanwhile, China is rapidly building new reactors and locking in uranium contracts across Africa. Niger, which was a major supplier to France, experienced a coup in 2023 that disrupted supply chains overnight. Uranium isn't just an energy commodity, it's a strategic asset, and the countries that secure it now will have significant leverage for decades. The next nuclear era isn't going to look like Chernobyl or 3 Mile Island. It's going to look more like a shipping container. Small modular reactors, SMRs, are factory-built, scalable, and designed to be deployed in remote locations or industrial sites. Companies like NuScale, Rolls-Royce, and TerraPower are actively developing them. Advanced reactor designs like molten salt and fast neutron reactors could even use existing nuclear waste as fuel. Global uranium demand is projected to grow significantly through 2040 as countries recommit to nuclear as part of their clean energy targets. Even tech giants are signing nuclear power agreements to run data centers. Uranium was born in a star, buried in the earth, fought over by nations. And it may end up being one of the most important elements in humanity's energy future.